Hello, this is Mr. McMurray back again, and we're going to answer that question that we left you with. Basically, if you have two people kicking a football from both sides, is this going to be a action-reaction force or is it not? First of all, is the ball going to move? And the correct answer is, assuming that it's being kicked equally hard from each side, that it will not. It will not change. It will stay still. All right. And someone says, that's because you have action-reaction forces. They're canceling each other out, and that's why it's not going anywhere. But let's look at that. Okay. Foot A is exerting a force on the football this direction, and foot C is exerting a force in this direction. All right. They cancel each other out, therefore the ball does not go anywhere. However, the net force is zero. The difference between those two, they're going in opposite directions, so we subtract them from each other, and the ball is not going anywhere. However, these are not action-reaction forces because both of those forces are acting on the ball, and therefore they're acting on the same object. And action-reaction forces cannot act on the same object. So what we actually have are a pair of action-reaction. A is exerting a force on the ball, and B is exerting an equal and opposite force on foot A. Okay, over here on this side, C is exerting a force on the ball to the left, but B is also exerting a force on the foot to the right. So these are action-reaction forces, and the pair over here are action-reaction forces. Now, if we're looking, does the ball move or not, we're only looking at the forces on the ball, which would be this one, which is moving it to the left, and this one, which is moving it to the right. And they give us a net force of zero, therefore there is no acceleration or change in its speed, and since the ball was just sitting there to start with, it's going to be just sitting there afterwards. Okay, so what we actually have are a pair of action-reaction forces. And the reason the ball does not move, because as part of each of those pair, there's a force acting on the ball from each direction, and they cancel out with a net force of zero. But the ball being kicked from both sides, those are not the action-reaction forces. There's action-reaction forces on this side, action-reaction forces on this side. The two forces acting on the ball cancel each other with a net force of zero, so its acceleration does not change, and it just sits there. Okay, so that's a very kind of important point, even though it seems kind of self-explanatory. It's a little more complicated than it looks like at first. All right, now another example then, talked about in the book, and we're going to look at it real briefly here, is what if a horse is pushing a cart, all right, and we have action-reaction forces acting on it. So first of all, we have the horse pulling on the cart this way, exerting a force this direction, and the cart is exerting a force then on the horse in the opposite direction. Okay, so the horse is acting on the bridle here and pulling on the cart, and the cart is pulling back against the horse. All right, these are action-reaction forces, and since we know that they're action-reaction, we know that they are equal as well as opposite, and that means the net force between those two forces is zero. So the question is, how does the cart move forward? Because if they're equal and opposite, they should cancel each other out and have a net force of zero. Okay, interesting to point out, there are friction forces on the wheel where it rubs against ground, and ground pushes against the wheel, but there are also action-reaction forces, so they are equal. All right, but the reason it's going to move is that the horse is pushing against the ground, and he's exerting a force on the ground, and the ground is exerting a force on the horse in the right direction. Now these are action-reaction forces, so they are equal but opposite, but since only one of them is acting on the horse, it's going to push the horse forward along with him, the cart with it. Okay, now the horse is technically pushing the ground back, but the mass of the earth is so big it does not affect it, whereas it does affect the acceleration of the horse. And so that's what actually makes it move. It's not the horse pulling on the cart that makes it move forward. It's how hard is the horse pushing on the earth. Okay. All right. This is similar to situation if we're doing a tug of war. Okay. Anytime there's tension, a tension force on a rope or a string, whether it be a tug of war, sideway to sideway, like this, or whether it be I'd say something hanging from a weight hanging from a rope. Say for some reason we've tied a rope around a rock and it's hanging down. There's tension in it, and the tension force is the same at either end, where this is attached to the top or where it's attached down to the rope. There's equal amount of force pulling on both sides, but you have action-reaction. Same way with this tug of war. You've got a big strong man over here, you got a little girl over here, but the tension in the rope, the tension force has to be the same. So he is pulling and exerting a force in this direction. She is pulling and putting a force in this direction. But there's the same force at any point of the rope acting on it. Okay, same amount of tension force or actually acting on it. And so these forces cancel each other out. You cannot pull harder on the rope to win a tug of war because there's going to be the same amount of force either direction, and it's going to be action-reaction. They're going to be equal. The way you win tug of war is to push harder on the ground. So if you push harder on the ground will push back against you harder. Okay, whereas if she can't push against the ground very much, then the ground can only push back a little bit against her. And so that force pushing against, it's not going to help. Now actually push, okay. So she's going to lose the tug of war. Now, if you put socks on this guy where he could not get traction, therefore could not push very hard, okay, and you had, say, cleats over here so that she could dig in and push really hard, then his force pushing on the earth would be very small, if any at all, and therefore the earth would not be pushed back against him very much, and in this case, she might actually win the race. I know one time I impressed everybody, all the junior high kids, because I outpulled one of the coaches. He is much stronger than I was, but I just happened to have old man shoes, my black shoes, that allowed me to get more traction so I could push harder against the earth, and I ended up winning that time. Okay. Don't know if I could do it again. I had to have really good traction, apparently. All right. Now, a couple other quick things to think about this. This is also similar to what happens with the bird. Okay. Helicopter would be the same thing. Helicopter wings push air down. When they push the air down, the air also action-reaction pushes back against the blades and pushes it up. Same thing here. As a bird brings its wings down, it pushes the air down, but equal opposite reaction tells us that the air is going to push back up with equal force against the bird, and this is what will push the bird and keep it up in the air and give it lift. Okay. Now, some of this air that it tries to push down on will swirl around, and as it swirls around, it'll kind of rise back up like this, and if you're the bird coming along behind it, air will push you up a little bit better, and this is why birds tend to fly in a V shape, so that these little curling updrafts from the wings will help the ones behind them. And actually, it turns out this front guy doesn't get that help, so eventually he will come back to one of the edges of the wing, and a new person will move in, and they keep doing that so the lead bird doesn't always get tired. All right. Last thing is, can you hit a piece of paper as hard as a heavyweight champion? Don't know any of the recent ones, so we'll just go with Muhammad Ali. Who can hit a piece of paper? Muhammad Ali when he's at his prime, or me? And actually the answer is about the same. We can put about the same force on it. Now, the thing is this: you can only hit something as hard and exert as much force on it as it can enforce back on you. And if I have a piece of paper in the air, I can hit it as hard as I want, but I can't put any more force on it than it can push back, because for every action force there has to be a reaction force. And so I can only put as much force on the paper as the paper can put back on my hand. And if I have a floating piece of paper, then it can't do much. Now, if I hold that same piece of paper in front of a wall, ow, that's going to hurt, because now the wall is, paper's going to exert force on the wall, and it's going to push back, and the wall is kind of helping them supply the force. And no matter, the harder I hit it, the harder the force it is going to put back against me. Okay, and so that's going to hurt very much. So you see this boxer here, when he hits the big weight bag, it doesn't even move very much because it's so heavy. He can put a lot of force on the weight bag. But if he tries to hit a piece of paper, which cannot push back very much, then he's never going to be able to hit it very much. And you can hit just like a heavyweight champion and hit equally hard because of Newton's third law of action and reaction. All right, now that pretty much finishes Newton's third law. So just a quick summary, run back through Newton's three laws. They all kind of work together. And so sometimes we do a worksheet where it says, okay, which law does this have to do with? And there's usually one that's the primary law, the biggest law that's affected by it, but they all interact with each other because they all have to do with forces. They all have to do with mass and inertia. All those things can affect each of the laws, okay? But remember, Newton's first law is the law of inertia, which basically says the more we said that mass determines how much inertia an object is, and inertia is the fact that it does not want to change its motion. If it's moving, it wants to keep moving at a constant velocity, and if it's stopped, it wants to stay stopped, and it will do that until a force acts on it. Okay, then it will either slow down or speed up depending on the force, if it's in the same direction as the speed or not. If it's stopped, it wants to stay stopped until a force acts on it. If it's moving, it will continue to move at the same speed in the same direction, which is what a constant velocity means, until something acts on it and causes it to either change direction, change speed, speed up, or slow down. And that's basically Newton's first law. Newton's second law says that how much an object accelerates when a force acts on it, it's going to be proportional to the force. In other words, the bigger the force you act on it, the more the acceleration will be. But the mass will have an inverse relationship to the acceleration. The bigger the mass of the object, if you put the same force on it, it will not accelerate as much as an object with small mass. All right, and that's why even though we have equal and opposite forces on Newton's third law, they'll have different effects depending on the two objects, depending on the mass of the two objects. All right, which brings us to Newton's third law, action reaction. Every time a force acts on an object, that object also has a reaction force acting on it. They are equal and opposite, but they don't cancel each other out because they're acting on different objects. Okay, they never act on the same object. All right, and so, but there's always equal and opposite forces, and for every action force, there's an opposite reaction, equal and opposite reaction force going the opposite direction. All right, that will do that. We'll be back to you next time on Chapter 5.